Why does this simple string of notes feel so undeniably right? And why does this other one evoke something entirely different? It's not magic. It's something far more fundamental. Every sound we hear is, at its core, a vibration, a disturbance in the air, a pressure wave that travels to our ears. A microphone captures this. It sees pressure variations over time. The taller the wave, the louder the sound. The more squished together the waves, the higher the frequency and the higher the pitch we hear. Simple enough, right? But real sounds aren't often this simple. A single note from a guitar, a voice, or even a piano isn't just one perfectly clean wave. It's a rich, complex mixture. And here's where the deeper patterns begin to emerge. To unlock these patterns, let's simplify for a moment. Imagine a pure note, one perfect, unadulterated sine wave with a single frequency. As we move to higher notes, the frequency increases. But by how much? How do notes relate across the musical spectrum? There are notes in music that sound strikingly similar. Just one is higher than the other. This special relationship is called an octave. We say a note is one octave above another when its frequency is exactly twice as high. So, if a note vibrates at 220 Hz, the same note an octave higher vibrates at 440 Hz, and an octave above that, 880 Hz. Each octave is a precise doubling of frequency. In Western music, an octave is divided into 12 distinct notes, often called semitones. And here's the crucial part. Each adjacent note within that octave increases its frequency by the exact same multiplicative ratio. If doubling the frequency takes you 12 steps, what's the single step's multiplier? It must be the 12th root of 2, approximately 1.05946. This means if you multiply the frequency of a note by this exact value, you get the frequency of the very next note up. Do it 12 times, and you've precisely doubled the original frequency, landing you one full octave higher. So, if we know the frequency of one reference note, like A4, commonly standardized at 440 Hz, we can mathematically calculate the exact frequency of any other note using this powerful formula, where n is the number of semitone steps away from A4, positive if going up, negative if going down. Now, let's talk about something you've definitely felt in music, even if you didn't consciously know the math behind it. Mood. Why does one melody sound bright and happy, while another feels sad or mysterious? This often comes down to whether the piece uses a major or a minor scale. It's all about the precise mathematical intervals between the notes. A major scale follows a specific pattern of whole and half steps between the notes. This pattern creates intervals that include major thirds and major sixths, which mathematically are simple frequency ratios, giving the scale a bright, stable, and uplifting sound. A minor scale, on the other hand, slightly tweaks this pattern. This subtle shift alters some key intervals. Most notably, the third note of the scale becomes a minor third. From a mathematical point of view, it's these specific frequency ratios, how notes interact harmonically, that shape the emotional color. In major scales, many intervals correspond to simple, stable ratios like 5:4 and 3:2, which our brains perceive as consonant and pleasant. In minor scales, some of those ratios become more complex, creating a subtle tension or dissonance that we associate with sadness. Remember that complex sound wave we saw at the beginning. the one that wasn't a perfect sine wave. How do we break that down into its pure note components? This is where a truly revolutionary mathematical tool comes in, the Fourier Transform. In essence, it's a mathematical microscope that takes any complex wave, no matter how messy, and reveals all the simple sine waves that add up to create it. It allows us to go from a wave's shape over time to a spectrum of frequencies, showing exactly which pure notes are present and at what loudness. It's how synthesizers work, how audio engineers mix music, and how we can truly understand the hidden architecture of sound.